Here's a problem that's a very difficult type problem. It's a two-dimensional elastic collision, or a glancing collision. And the thing that makes it difficult is it also has unequal masses. So here we have a neutron moving at a very fast rate to the right at 4.5 times 10 to the 5th meters per second. And it hits a helium nucleus, which is 4 times more massive than the neutron. They glance off of each other. The helium nucleus careens downward after the collision at an angle of 45 degrees. So we're given that. And then the neutron, after collision, it moves upward, and we don't know what that angle is. So we'll call that angle theta 1. We don't know what that is. We know what theta 2 is. That's 45. That's the angle that the helium nucleus takes. Thinking in terms of momentum, remember I like to at least use v for the velocity before collision, but then u for the velocity after collision. So for the neutron here, we'll call the velocity after collision u1. We don't know what that is. That's one of the things we want to find. And then the velocity after collision of the helium nucleus, we'll call that u2. We don't know that either. So so we can say, given that we have the mass of the helium nucleus is equal to 4 times the mass of the neutron, then we see the relationship there. It's just a 4-to-1 ratio, right? Okay, so we can just use 4 for the mass of helium and 1, the number 1 for the mass of the neutron from now on. So that's one thing that's given. We also know that the velocity of the neutron, we'll call that v1, before collision, is equal to 4.5 times 10 to the 5th meters per second. We also know that the theta of helium, we'll call that theta 2, is equal to 45 degrees after the collision. What do we want to find? What we want to find is the theta 1, which would be the angle that the neutron takes after collision. And we also want to find out the velocity of the neutron. We'll call that u1 after the collision. And we also want to find out u2. That'd be the velocity of the helium nucleus. So given these things, let's try to find these. Now, probably on the AP test, they would give you one more bit of data to make the, because the math on this one's pretty tough. Okay, so I don't think that they would give you this difficult of a problem. However, it's nice to see how one of these is done, so you know it's actually doable. Alrighty. Oh, I forgot to mention one thing. The velocity of the helium nucleus before the collision, we'll call that v2. That's equal to 0. Okay, so v2, the velocity of the helium before collision, is equal to 0. We need to have that. Okay. So I'll just put a line there, and we can keep referring back to this diagram. Now, the first thing I'd like to note is that this is an elastic collision. So the kinetic energy, the total kinetic energy after the collision is the same as before. So we can say then that, okay, 1/2 the mass of the neutron, I'll call it m1, times v1 squared, so that kinetic energy before collision, plus the kinetic energy of the helium nucleus before collision, since it's not moving, that kinetic energy is 0, is equal to 1/2 m1 u1 squared, the kinetic energy of the neutron after collision, plus the kinetic energy of the helium nucleus after collision. Alright, so M1 refers to the neutron, M2 refers to helium. Okay, so we have that. We can divide out all the halves, and we can replace the masses with just either a 1 or a 4. So this is equal to 1 here. Oops, sorry. Pesky lights. I'll turn on the little lamp here, so in case the ceiling light goes out again, at least we'll have a little backup. Okay, so the mass M1 is 1 unit worth, and then the mass of the helium nucleus is 4 times heavier, so I could just put that in there. And so we'll simplify this. 1 times V1 squared is just V1 squared plus 0, that's just nothing, equals, okay, U1 squared plus 4 U2 squared. I think probably the most complicated an AP problem would be is they might give you a glancing collision where the masses are the same mass, same size mass. So in that case it would be V1 squared equals U1 squared plus U2 squared. Okay? But in this case it's a little harder. We have different size masses, unequal masses. Alrighty. So this is the result from the law of conservation of kinetic energy. So I'll just write that as a reminder next to it. So that's our first equation. Now this is a two-dimensional problem, so it's one of those situations where we have to break up the momentum into both x momentum and y momentum. Okay, so let's look at the conservation of momentum in the x direction, if you want to call it that. Okay? We know that M1 V1 before collision, in other words, plus the momentum of the helium, which is 0 before collision, so this is before the collision, is going to be equal to the total momentum after, which would be equal to M1 U1 cosine theta, because remember now we need to think in terms of the horizontal components, the x direction here. And if we look back up here, and I'll just use, we could say that this top vector here has a horizontal component and a vertical component. This is angle theta. This horizontal component here is the cosine component, right? This vertical component would be the sine component. So anyway, getting back down to our equation, or our conservation of momentum in the x direction, the momentum before is equal to momentum after. So this is M1 U cosine theta 1 plus M2 U2 cosine theta 2. We just have a lot of terms. That's what makes it fairly tough. Okay? So if we simplify that a little bit, we can, and remember M is 1 unit's worth and M2 is 4 units worth, so we'll just simplify that down. We end up with V1 equals U1 cosine theta 1 plus 4 U2 cosine theta 2. Okay? Now, from experience, having messed up many times in the past myself, I know that eventually I'm going to be using a trig identity, sine squared theta plus cosine squared theta equals 1. And if I arrange this the wrong way, then the angle I'm looking for will drop out. So what I want to do is I want to isolate theta 1. Okay? and get everything else over on the other side except for maybe like U1. So I'm going to take this, otherwise it's going to disappear due to the fact that I'm going to be using a trig identity. So I'm going to rearrange this, basically subtract 4U2 cosine theta 2 from both sides. So I'm going to get V1 minus, now I'm going to subtract that from both sides, so we get 4U2 cosine theta 2, and set that equal to U1 cosine theta 1. Now we have this theta 1 isolated over on one side, and that's good because we want to know what that is. Over on this side, that theta 2 is actually going to be able to be canceled a little bit, or at least this one won't cancel. Okay, so this is a good result right here. So what do we have so far? We have result number 1 right here as a consequence of the conservation of energy, and we have equation 2, or result 2, as a result of the conservation of momentum in the x direction. Okay, now let's repeat the process for the y direction to get a third equation. So we'll look at the conservation of momentum in the y direction. Okay, now if you think about it, take a look back at our original drawing. Both the neutron and the helium nucleus are going to be going off opposite directions, right? The momentum in the y direction before the collision was 0. So, therefore, the momentum after the collision in the y direction must also equal 0. So that means that this component and this component of momentum, in terms of momentum, are going to be equal. Okay, so we can say the momentum in the y direction before the collision is equal to the momentum in the y direction after. The momentum in the y direction before the collision was 0, and the momentum after is what? M1 U1 sine theta 1, okay, minus M2 U2 sine theta 2. And now remember, we can simplify, like M1 is 1 unit's worth and M2 is 4 units worth. So I'll just add this to both sides and we get 4 U2 sine theta 2 equals U1 sine theta 1. And there's equation 3. Okay, using the idea of the conservation of momentum in the y direction. In the y direction, since the neutron was the only thing moving at the beginning, and it was only going in the x direction, there was no y momentum before collision. Therefore, the sum of the momentum in the y direction after collision has to also be 0. Alright, so far so good. Well, let's move on now to, this will enable us, since we have 3 equations, to solve for 3 unknowns. So we now can solve for our 3 unknowns, since we have 3 equations. What are our unknowns again? Theta 1, U1, and U2. So this, but it's not an easy task. Okay, let me get the light back on. Alrighty, so what's next? Well, quite a bit. What we need to do is look at equation 2 again. Just a reminder, equation 2, that's this one. I'll write it back down. And we want to square both sides. So square both sides of equation 2. Okay, so let me write equation 2 down. So V1 minus 4U2 cosine theta 2 equals U1 theta 1. Now let's square both sides. Okay, so I'll just go ahead and I'll use a red pen to kind of highlight. So we'll square that side and we'll square this side. Okay? When we do that, and I know you guys know how to FOIL and square and so forth, we end up getting, so I'm going to I'll just do this first one. So I'll expand this out, V1 minus 4U2 cosine theta times V1 minus 4U2 cosine theta 2. Okay, so that's just this left-hand side squared, and that's equal to V1 squared minus 8V1U2 cosine theta 2 plus negative 4 times negative 4 is 16 U2 squared cosine squared theta 2. So that's the left-hand term squared. The right-hand term squared would be U1 cosine theta 1 times U1 cosine theta 1. So that's equal to U1 squared cosine squared theta 1. Alrighty. So that's, see all the little algebra headaches we have for this. So all I did was square both sides of that first, of equation 2, I should say. Okay, so we can call this number 4 if you want. Number 4. Okay, now let's square both sides of equation 3. Okay, now looking back at equation 3, I'll just write it again. We have 4U2 sine theta 2 equals U1 sine theta 1. That just came from the conservation of momentum in the y direction. So now let's square both sides. I'll just highlight that in red. And when we do that, we get 4. I'm not going to expand it out like this. You know how to do that. So that'd be 4 times 4 is 16. U2 times U2 is U2 squared sine squared theta 2. And on the right hand side, that'd be U1 squared sine squared theta 1. Alright. Now where are we heading with this? Okay, we'll call this number 5. Well, it turns out this is just basically a routine. It's the routine that allows you to get through the algebra without a fatal attack of where you'll freeze up and you won't be able to move on. Okay, so now if we take and add both equations 4 and 5 together, so now let's add equation 4 and equation 5. And then we're going to use a trig identity, which you're well familiar with, sine squared theta plus cosine squared theta equals 1. Then we'll make some progress. Okay, so let's add this equation here with this equation here. So we'll take the left-hand stuff and add it to the left-hand stuff here. And then we'll take the right-hand stuff of equation 4 and add it to the right-hand stuff of equation 5. Okay, so what I'll do is I'll just put the equation 4 stuff down first. V1 squared minus 8. Oops, I'm running out of this room here. Okay, V1 squared minus 8 V1 U2 cosine theta 2. I won't talk. You just watch. Plus. Okay, that's a left-hand term. Now I'm going to add the left-hand term from equation 5. So plus 16u2 squared sine squared theta 2. Ooh, I see a cosine squared theta 2, a sine squared theta 2. That looks like prime material for this trig identity right here. Okay, and now we'll set that. We've added the left-hand terms of both of these. Now we'll add the right-hand terms. So the right-hand term here is u1 squared cosine theta 1, and then the right-hand term for the equation 5, so plus u1 squared sine squared theta 1. Okay. Alrighty, so now we can simplify this. I'll just write out the things we can't let's take a look here. Here we have 16, that's good. We can factor out the 16 u2 squared, and there's that cosine squared theta 2 and sine squared theta 2 right here. So those are added together to form 1. So really then we have, this could be v1 squared minus 8v1 u2 cosine 2 plus 16 u2 squared times 1, or just that, equals, now this side, oops, I forgot to write the squared in there. This side we have the same situation. Notice we have a cosine squared theta 1 here and a sine squared theta 1 here. So there, that can be you can apply that trig identity to this side. So that would just be u1 squared times 1, or just u1 squared. Okay. So now we have that simplified, and we can call that equation 6. Alright. Well, we're not done yet. Okay. Now if we combine this equation 6 and all the way back to with equation 1. So now let's combine equation 6 with 1. And if you think back, 1 was the result of that law of conservation of energy. So 6 looked like this. We have v1 squared minus 8v1 u2 cosine theta 2 plus 16 u2 squared equals u1 squared. And then equation 1, if we look back, it's v1 squared equals u1 squared plus 4 u2 squared. Now we can combine these and use maybe like substitution. Use substitution. What I would probably do is I'd take this is v1 squared and that's v1 squared, so I can just substitute this in right here for v1 squared. Okay, so we end up with u1 squared plus 4u2 squared, that's what I substituted in for that, minus 8v1u2 cosine theta 2 plus 16u2 squared equals u1 squared. Okay, and if I see that we have like terms here, u1 squared on both sides, so I can subtract u1 squared from both sides. That gives me 0 on the right, and we end up with just the remaining material here. Okay, and I see here that we have 4u2 squared and we have 16u2 squared, so 4 and 16 is 20u2 squared minus 8v1u2 cosine theta 2, and that's equal to 0. Okay, so we've simplified that down quite a bit. what we did is combine equation 6 with 1 and simplified it down as much as we could. Well, maybe I can just, since we can move this over to the other side, we get 20u2 squared equals 8v1 u2 cosine theta 2. Okay. Well, that's pretty good. And we have some things that we already know, right? So let's try subbing in what our givens are. So try subbing in our givens. Remember what our givens were? Okay. Well, we know what V1 is. And we know what theta 2 is. So let's at least get those things plugged in. So, okay, 20u2 squared equals 8 times, that V1 was 4.5 times 10 to the 5th meters per second, times u2, and the cosine was 45 degrees. So I've substituted in the 45 degrees here, and the 4.5 times 10 to the 5th, the velocity of the neutron before it hit the helium nucleus. If we go ahead and simplify this, I'll just write it down. 52, okay, u2. And now I can divide both sides by u2. And that'll give us 20u2 equals that. So basically, divide both sides by u2. We get this. Solving for u2. We get this. So now we got one answer here. We got the velocity of the helium nucleus after collision, 127,260 meters per second. So yay, we got something. But it took us 3 pages to get to. Okay? So that's good. Okay. We still have a ways to go, though. Now what we need to do is take that answer and sub that answer, that U2. So now we want to sub our answer U2, which was 127,260 meters per second, into equation 1 again. And just as a reminder, and that will allow us to get U1. Okay, so let's take a look. Let's look at equation 1 again. That was V1 squared equals U1 squared plus 4 times U2 squared. And it's only the U2 that's squared, not the 4. Okay, so let's go ahead and sub our value that we just got here in for U2 right there. And we already know what V1 is. V1 was given. That was 4.5 times 10 to the 5th right there. So we'd sub that in for V1. And that way we can get what U1 is. I'll just rearrange it. U1 squared is equal to what? V1 squared minus 4 times U2 squared. Okay, so now we can just go ahead and continue the process here. I'll plug in my 4.5 times 10 to the 5th for V1. I need to square that. Okay, and then minus 4 times U2, and the U2 I'll substitute that in, 127,260, and I need to square that. Okay? So, what do we get? Well, if we go ahead and do the math, that would be the neutron speed after collision. It turns out that's equal to 371,106 meters per second. So we got another answer. Good. We just have one more thing to go, and that's to get theta 1. So we still need to get theta 1, which is the angle that the neutron glances off after collision. So we need to substitute our information back into some equation that has an angle, like equation 3. If you think back to equation 3, that was 4 U2 sine theta 2 equals U1 sine theta 1. Okay? And we want theta 1, right? So let's isolate sine theta 1. So I'll divide both sides by U1. So we get, therefore, sine theta 1 equals 4 U2 sine theta 2. We already know those. Divided by U1. Okay, and we already know U1. So let's go ahead then and plug that in. So sine theta 1 equals 4 times 127,260 times the sine, and theta 2 is 45 degrees. Okay, all divided by U1, which is 371,106. So when we do that, we get sine theta 1 is equal to 0.9699. And if we take the inverse tan, theta 1 would be, inverse sine of 0.9699. That's equal to 76 degrees. So that is theta 1. So in summary, and we're done. Can't believe it. Okay, in summary, we had that neutron moving at a very fast rate, hitting a helium nucleus with a glancing collision. The helium nucleus was at rest at first, but then the helium nucleus went off one way, and the neutron went off another way. Okay, the neutron went off with a speed of 371,106 meters per second. The helium nucleus went off after the collision at a U2 of 127,260 meters per second. The angle here was given as 45 degrees. We found the angle that the neutron took from the horizontal is 76 degrees. Okay, and remember, this is the hardest type of problem. On an AP test, you would be given at least one more variable, and that would cut down on the math considerably. Thanks a lot, guys.